instead. And hopefully I remember to upload the video after the lecture. So we are somewhere here at the piecewise definition of continuously differentiable functions. So we have the zero, first, and second order derivatives here. And we assume that the function itself, its derivative and second order derivative, shall be continuous on this interval. Meaning when I get this function, there is something continuous. So in principle, I can take the derivative of this function again and I get a value. Now, it's very important what we do next, because we can demand that the value, gradients, and curvature at different intervals match. I'll give you an example. Let me see. Actually, the examples are given below. But let's say here, I have one function, very nice. It's continuous, it's differentiable. If I say here's my interval and the next function starts over here, both functions are continuous, the derivatives can be taken, but at this very, very important part, right, where the two functions meet, they're not continuous. So what I demand is that at the interval boundaries, the function still should have the same function value, the same derivative, and the same curvature. Now, when I demand these things, I actually can express this in a system of equations, saying matching intervals and matching derivatives. Sorry, matching derivatives, values, and curvatures at the interval boundaries. So I demand that the derivative for Si at a certain place, or at the end of the interval, is the same as for the previous segment at the same position. I also could write here that the xi plus 1 at si equals si plus 1 at xi plus 1. But in this definition, I just have one less to write. No, we don't need to look for this. We know this. And I demand the same for the curvature. Now, very careful, the xi here refers to the piecewise defined interval boundary. So for every boundary, I can select this point connecting two intervals. Okay, so we match function values, we match gradients, and we match curvatures at these points. In the figures, I do not match function value on the left. I do not match derivative, and I do not match curvature. Right? So these are not given. What we want is the exact opposite. Matching value, matching curvature, matching derivative. Right. So we can actually show that the parameters of my piecewise defined polynomial are well defined through the measurement points M. H as a difference between interval spacing. So in this notation, I actually never really properly define what's M1 and M2. Did I? so maybe I need to, well, I should provide MI definition in detail. No note. Need to add this later, maybe after the lecture. So some homework for me. Not a problem. And what we should get at the end is some well-defined smooth function through this interpolation. Now there are some limitations, but there are some advantages as well, because we do not run into very, very crazy extrapolation catastrophes. Now moving on. How to do this in SymPy? We again work with the interpolant or interpolate a 1D interpolant. So this is inter p1d, and the function call is pretty easy. We provide the data points as x and y, and we specify the kind that is by standard linear, but we can change this to cubic, which gives us our cubic spline. We can have a quadratic one as well. Now, examples. What do? We interpolate the function. We define an x and y array. Here, the cosine. Well, the cosine of the square of x. That will be interesting. And then we perform 3 different interpolations based on a linear, quadratic, and cubic spline. And then we plot. So first of all, this is a very, very interesting function, no? Let's see. Endpoint, let's say 20. Okay. Need to adapt more. Change now. Here. 2020. Oh, so interesting. Okay, so what do we have? We have the data points, blue dots. The blue dots now connect, or are connected, I should say, between our interpolations. We have a linear one, that's the orange curve. And we see, oh, there are big mistakes. Then we see the quadratic fit, well, that looks a little bit more like it. And then the cubic fit, that looks like the smoothest of all. Now 41 points are not too many. A little bit more. Now the question is, where do we actually plot the real data? I just showed you the interpolation. How do we judge the quality of the interpolation? Well, we would need to define another array. Let's do this over here. That is a little bit more densely sampled. Maybe 401 points. Extend, then we plot this as a black curve. How about that? And what we want to see is basically no difference between actual and interpolation. So, uh-oh. Is this good? Is this bad? What's going on? We talked about interpolation, right? And I give you the interpolants as colorful curves. The data point at colorful blue dots. And then I say, wait a moment. How do we know if the interpolation is good or bad? Then I say, we need to compare it to the actual curve, right? But I never showed you the actual curve. So what I did is I took a function I used to synthesize my data. That is some cosine of minus x squared divided by 9. Okay? And then I plot this as a black curve. And then I see the black curve. I was like, the blue dots are still on my curve, right? This is very good. So I didn't do a mistake generating my artificial data. But the interpolations look like, do they look really good? Do they look like still okay? Or do they look like absolute crap? Who understands what I want? Hence, who thinks this is a good plot? Good interpolation, hence not up. Who thinks it's a good interpolation? Hands up. Who thinks it's a okay interpolation? Who thinks this interpolation is good? Who has? Very good. Everybody else, no opinion. So this interpolation is clearly not good because the sampling of the data is not dense enough. And you see very clearly here at the bottom, right? The data point sample almost a linear part, but there's a lot going on in the actual data. So this is not how you use interpolation. You must be very careful, right? Doing nonsense is quite easy. But we are scientists, and are there famous scientists that are known for nonsense? Maybe, right? But well, actually there is, but normally when scientists create a lot of nonsense, it's quite harmful. So we must be really, really careful in what we do. So we either sample our points more densely, tada, or we right, always question what we did, always try to verify as much as possible. Right? As dense as possible, not as dense as needed. Okay, and if there are no comments or questions, then I would say close the interpolation here. I must do some homework, giving you what is M in definition, right? But there are some, it will be related to the data points provided. Obviously, M might be a middle point or something like this. And then, so whatever you do in Python, it's quite easy. Python is basically programming glue that puts together different capabilities. We have access to a lot, integration, differentiation, equation solving, interpolation, right? Regression fitting. But you need to know what you do. You need to understand what are the basic ideas of the techniques and be aware of the pitfalls there could be. Because if you don't know the pitfalls, you will trap into them, right? And then you produce nonsense, and you will be famous for producing nonsense. Or not, right? Okay, comments, question. If there are no comments or questions, then we continue with student presentations. Well, sorry, yeah, there are still students, but TA presentations, and all the luck for the final exam.